So take it away, Isaac.
Hey, Aaron. Thanks. Okay, so in this talk I'm going to explain what path optimization is and how you can use it for cold spray. And I'm also going to talk about some applications of path optimization for additive manufacturing and structural repair. So path optimization is the process of determining the robotic motion to fill a desired volume with cold spray while optimizing the efficiency of the spray process, the geometric error of the deposit shape, and or the structural integrity of the resulting part. Optimizations of path optimization include cold spray additive manufacturing. This is a topic that I presented on at last year's CSAT, but it can also be used for structural repair. And in particular, I'm going to give a couple of examples of edge restoration and spiral infill. So over the past few years, I've developed an algorithm for generating and optimizing paths for cold spray on irregular surfaces. It starts off by inputting the substrate or the initial surface, which is given by the solid black line, and also the target surface, which is given by the solid blue line. And then you generate intermediate layers between the target and the substrate surface, given by these thin black lines. And these intermediate layers are generated based on some target layer thickness. Then in the second step, for each one of these layers, you generate a path that covers that surface area. So in this illustration, the nozzle path is given by these black arrows. Each arrow represents a line of nozzle motion that moves in or out of the page. The base of the arrow is the position of the nozzle, and the direction of the arrow gives the orientation of the nozzle. The length of the arrow represents the time that is spent over that area. So the longer the arrow is, that means the slower the nozzle is moving. The predicted deposit from this path is given by this slashed red line. And inevitably, the simple path that you generate in this step will not result in the prescribed layer thickness unless you have a very good first guess. So that's where optimization comes in. In step 3, the nozzle velocity along each line is corrected to reach the desired layer thickness. This is done using a gradient descent optimization. Now the slashed red line overlaps with the targeted layer surface if you've done things right. And in general, the velocity is slowed down, which leads to these longer arrows over where the areas where the thickness deficit is the greatest, and it's sped up in areas where there's too much thickness. And then the final step is to combine the path from each layer into a single path and export to robotic program. So we've developed a high curvature coupon to test the effectiveness of this algorithm. The coupon was designed to press the limits of what is possible with cold spray. The initial surface has a 0.5 millimeter radius of curvature at this corner. And to put that into context, we sprayed this coupon with a nozzle that has a 5 millimeter exit. So as you can imagine, that poses a big challenge because as you're spraying directly on the corner, much of the material is going to come out of the nozzle and hit elsewhere on the surface at a high angle. So this slide shows what the model predicts for a couple of different cold spray strategies. On the left is a more conventional strategy in which the same path is used on each layer and there's no velocity correction. And on the right is the result of the path optimization algorithm. So what you can see here is both strategies do a pretty good job in the flat areas of the surface, but there's a major difference around the corner. And if we zoom in on the corner, we get a better image of the difference between the two strategies. The conventional strategy resulted in this significant thickness deficit around the corner. And again, this happens for a couple reasons, because the plume is so much wider and much of the material misses that corner, and also because the path is not updated in between layers. And then the optimized path results in a final deposit that's nearly indistinguishable in between layers. And if we look at the nozzle trajectories, we can better understand how the optimization works. Again, so these arrows are the nozzle positions, and the motion is in and out of the page, and the length of the arrow represents the time that is spent over that area. So in the conventional strategy, all of the nozzle velocities are constant, and the nozzle positions are not updated to reflect the new surface, whereas in path optimization, the velocity has been lowered around the corner to compensate for the lower material deposition, and the nozzle positions are updated to reflect the surface of the previous layer. So what you saw so far was the model results. Here is what actually happens when you use that optimized path. An image of a real deposit is on the left and the target is on the right. Overall, this was very good for our first result. So the slope of the deposit matches very well, and we were able to build a thick deposit around this 5 millimeter radius of curvature corner. Although not quite as thick as prescribed, but still better than what would have been done with a conventional strategy. And when we tried to assess what caused this thickness discrepancy, we noticed one key indicator of what went wrong. So the discrepancies are asymmetric. They're not mirror images of one another. If the problem was solely with the optimized path, we wouldn't see an asymmetry because the path is symmetric. So rather, this discrepancy indicates a robotic tool control point misalignment. And this is basically what happens when the actual center point of the nozzle isn't located where the robot controller thinks it is. So to test this hypothesis, we tried introducing a few types of simulated alignment error into the model, and we were able to generate a resulting deposit that is qualitatively similar to what was observed. That's what's now shown on the right. And if we zoom in on the corner, we can better compare the two. The simulated results in a similar qualitative shape and thickness deficit of about 1 millimeter. So this result shows how critically important robotics alignment is when dealing with such small features. And we're taking steps currently in our lab to improve the robotics alignment procedure so that we can then evaluate the effectiveness of the path optimization algorithm. Okay, so next I want to talk about how path optimization can be used for structural repair and in particular edge restoration. So in an edge restoration, I'm talking about any situation in which you want to apply a deposit to a substrate and maintain a sharp 90-degree edge. So as anyone with practical cold spray experience knows, if you apply cold spray up to the edge of a substrate, you will get a gradual taper, as shown here. But one potential way to avoid this taper is just to wrap the cold spray around that corner. But to do that, you need the path optimization procedure. And then after post-machining, you still have that taper present in the conventional strategy, whereas you get the nice 90-degree edge using the optimized deposition. Okay, so this is a look at what path optimization would look like for edge restoration. On the left is what happens when you regenerate the path for each layer, but you skip the velocity correction. And on the right is the complete path optimization algorithm. So as you can see, simply regenerating the path after each layer is not enough by itself to reach the targeted deposit surface. And if we take a look at the path velocities, we can get a better idea of how the velocity correction works. On the left, all the velocities are constant because no correction was applied. On the right, the velocities are variable, and the gradient descent optimization leads to an interesting pattern. So contrary to what you might expect, the slowest velocities are not right in the corner, but rather in this area on the edge. And the reason for that is because if you overcompensate directly on the corner, you're going to get too much material depositing here, which would cause shape distortion. But if you overcompensate on the edges, it leads to less shape distortion. But then because you overcompensate in this area, you have to undercompensate here, and that creates a ripple effect that kind of goes down the line. So now if we look at how this deposit will look after post-finish machining, we see that we get that 90-degree edge that we want, but more importantly, the layers are nearly flat at the newly machined edge of the part. So this means that we should expect the microstructural characteristics to be similar at the edge as they are in the middle. And we shouldn't expect any significant drop-off in mechanical properties, which is very important for structural repair. And then I also want to highlight the additional capability of using this algorithm to predict some spatially varying properties that result from the motion strategy. So this plot shows the weighted average impact angle on each layer, and 0 degrees from normal is given by green and 45 degrees is given by red. And as one would expect, there's a higher concentration of high angle deposition centered on the corner of the part. So depending on the material and objective of the repair, high angle impact can be either good or bad. This algorithm offers the ability to optimize the path with respect to minimizing or maximizing the presence of high angle impacts. An average impact angle is not the only quantity that can be measured. Things like the average plume position, particle size, or impact velocity can also be measured if the spatial distribution of those properties is known within the flow. Okay, and then the next application of structural repair I want to talk about is spiral infill. In a spiral infill, you have some localized damage on a surface. You blend out the damage with a spherical head cutting tool, and then fill back in with cold spray. And under a conventional approach, the material would be filled in by some basic raster pattern or with constant velocity and would result in this mound-like feature, whereas with path optimization, the divot can be filled with minimal overfill. So then after post-machining, the amount of material waste is mitigated. So I've applied the path optimization algorithm to a hypothetical blend out. The top image shows a spiral path that is generated to cover the area. The bottom left image shows what the predicted deposit would look like by the conventional approach in which no velocity optimization is performed. And then the bottom right image shows predicted deposit when using the path optimization algorithm. So that wraps up my talk. Thank you for inviting me to speak at this year's CSAT, and I'd like to open it for questions.
All right, thank you, Isaac. So we have a couple questions that came in. First, does your algorithm take into account things like residual stress that may change with differing velocity?
So I have a separate model for modeling residual stress, but it's not integrated with the path optimization model. That being said, if you had an idea, if you had some first principle model of how residual stress is induced by varying impact velocity, then that's one of those things that you could use that color map for to get an idea of how the residual stress varies within the deposit. And then you could plug that into another elastic deformation model to see how the residual stress affects the shape.
Okay, so another question that came in, is there any accounting for the actual velocities of the robot? So the kinematics of the robot, are they included somehow in this, or could they be?
No, they're not currently. So these are the velocities that we are prescribing to the robot, and but in terms of the actual kinematic model and how the robot will respond to those commands, that's not currently integrated. Okay.
So that's about it for time. Thank you, Isaac. Good